Today we're creating a very simple game called Game of Life. Game of Life is a cellular automation zero-player game. It means that no player inputs are required. The game was created by British mathematician John Horton Conway in 1970. The game output is determined by the initial state of each cell. The rules are extremely simple. A cell has two possible states: alive or dead, populated or unpopulated. Each cell interacts with its neighbors, which are cells that are located at the bottom, top, left, right, top left corner, top right corner, bottom left corner, bottom right corner. And the state of the cell is determined by the following rules. Any live cell with fewer than two live neighbors dies for underpopulation. In this case, we're alone in this cold and lonely universe. We die. Any live cell with two or three live neighbors lives onto the next generation. Oof, God, we are safe. Any living cell with more than three live neighbors dies for overpopulation. Not much food and not much air, we die. Any dead cell with exactly three live neighbors becomes alive by reproduction. Just a small reminder that life is magic. Hardware-wise, we're using an ESP32 board and a small 128 by 128 OLED screen controlled by a SH1107 driver. The way we print to the screen is by sending commands over I2C. For example, for printing a single pixel to the top left corner of the screen, we have to send the following commands in bytes. We are sending x value B0 for the column position, 00 for the row position, 10 for the page number, and 80 for the data that we're printing to the screen. We have to understand that we are always sending byte-sized packages. So for example, if we send x value FF, it will look 11111111 in binary, and that will print an 8 pixel long line. Another example, if we send x value AA or 10101010 in binary, that will print a dotted line. In motion, it will look like this on the screen, printing bite-sized 8 pixel lines one at a time, changing rows every 16 columns, pages every 16 rows. I will speed up the process, but you get the point. To create the game, we are using a very small universe, a grid of 16 by 16 with 256 possible slots, and you probably notice that this makes each cell 8 by 8 pixels across. It will look like this on the screen. One cell will use 8 bytes stacked vertically. Nice, we now understand the rules, how the screen works, or how much data each pixel is using. Now let's jump into the code and analyze the logic. Let's start with the game logic. For that, we only have two different files, all of them very simple. The first one is the SH1107 file, that's for having our screen driver. Then we have our main code in our main.py. If we start on line number 6, we're basically initializing our I2C bus with a baud rate of 400,000. We're initializing our screen driver, we're clearing the display, setting the display to vertical mode, and setting the contrast level to 128 of 255 possible values. Let's also as a reminder, this is a black and white screen, so we are only setting basically the brightness of white. Then we are creating 3 different lists of our OR arrays. Let me just add here the list. The first list is to hold the current frame, so the frame that's going to be printed on the screen. Let me just show you one example here. For example, here, this is the all possible values, or how to basically print each pixel on the screen. So we have 2048 possible values. So we have to create an array that will hold all those possible values in if we want to print on the entire screen. Then we have another list for holding the current game logic. So again, if I switch to Excel, this is my universe, my my cell universe. As you can see, it's divided by 16 wide by 16 tall square. So this is my universe, and it has 256 possible values. Then we have another list with also the same number of possible values, 256 possible values. And the reason of having two lists, it's one for holding what's the current state of my cells, if they're dead or they are alive, and the new one, or the new game logic, or line number 16, is to basically from the current game state create the new game state. So for example, if I'm here alive, what's gonna be my next state based on my current state, based on my current position, if I'm gonna be alive or dead. Then we're creating a glider. A glider is this shape. So if I'm just gonna hit start, so as you can see, it's a live cell, or a collection of different cells that spawn different cells, and it's creating the illusion of movement. Perfect. Now I am also giving you the option to create a tumbler. Then we have our functions, methods, one for render current frame, getting next frame, deciding if the cell is gonna live or die, getting the number of neighborhoods, and our main game loop. If we take a look at our main game loop, first we are just waiting for 1 second, then getting the next frame, obviously, so we have cells in current state, so obviously the next thing that we want to do is calculate the next frame based on our current position. So if we open that function, it's basically just a for loop of what's currently going on the screen and deciding if the cell is gonna live or die. So step number 1. Let's suppose that we are here that we have one cell in 123. Let me just change the color to yellow. And the next thing that we have to do is basically know exactly the state of my neighbors. Just color. So once again, we're cell number 123, and we need to know exactly what's going on around me. So for that logic, we have this example. If we open that in a Python interpreter, let me see, 123. Okay, 123. So 123, it says that the down cell, or the cell that's below me, it's the cell number 123. My the cell that I have on the top, it's 107, left 122, right 126, left top corner 106, 108, and you get the idea that we are basically getting a hold of that cell position, or the position in that list, and we're just getting that value. So the code is extremely simple. It's basically just, for example, if I'm 123 and I want to calculate what's the position that's below or at the bottom, so it's basically my current position plus 16, so it's 139, and we only have here a condition to know if we are at the limit of our list. So for example, if I'm greater than 255, we basically have to start from the top and plus the remainder. So if I'm, for example, 251, and I want to calculate my position that's at the bottom, I will have to respawn on the top. So that's number 11. So 11 is down. and so forth. So my top left is 10, top right is 12, so you get the idea. So that's the reason of using the modulus for calculating or for getting new positions if we somehow end up at the end of the list, at the beginning of the list, at the sides of the list. So if, for example, if we are in position 127 and we want to calculate what's the cell at my right, and if we are on the left side, that will also apply. So that's the reason of having the modulus for calculating that position. So if we go back to our code, so okay, so first live or die. First, we get in our neighbors that we already established is that, okay, it's based on my current position plus 16, minus 16, minus 1 plus 1, and so forth for having the positions. Then we only have a small logic to know if we run out of space and we have to spawn bottom, top, left, or right. Then we are basically just looking at my current game position and knowing exactly if that cell is occupied or not. So if we have a living neighbor or a dead neighbor, and based on that we know exactly how many neighbors we have. So for example, okay, someone it's at that position, yes, okay, so let's add another let's count plus 1 to that, to the counter of how many neighbors I have. So and so forth. So we repeat that same process for each position. So for 256 possible values. And then we have logic. So if we have more than 3 neighbors, okay, we're dead. If we have less than 2 neighbors, we're also don't do anything, so we're dead. Else we're alive. If we are dead and we have 3 surrounding neighbors, we come back to life. Else we are dead. So that's the logic. So if we have more than 3 neighbors, we're dead. If we have less than 2 neighbors, we are also dead. Else we are alive. This is the condition if we are alive and we have the X number of neighbors. Else, if we are dead, and if we have exact number of neighbors to be equal to 3, then we go back to life. So that's the life or die condition. And that's it. That's it. It's extremely simple, nothing crazy, and you can basically experiment with this logic. And I hope that you learned something and that you like the code.